Welcome back to a course on calculus, limits and continuity. In today's lecture, we are going to see a new topic, that is monotonic functions. Right? Let me give you proper definition of a monotonic functions. Hope we are aware of these things, but still let us see it in a proper way. So the definition tells you that f is a real valued function which is defined on a particular interval. Okay, so it is a real valued function on the open interval a comma b. Then this f is said to be monotonically monotonically increasing on ab if you have something of this sort. Implies f of x less than or equals f of y, and monotonically decreasing sorry monotonically decreasing if a less than x less than y less than b implies f of x bigger than or equals f of y. Okay, the definition that I have given now is due to Walter Rodin. Okay, if you see from if you see from the writings of other authors, you may see a monotonic strict increasing, monotonic strict decreasing, monotonically increasing. These there are four classifications. Actually, increasing is in strict sense and in usual sense. Strict sense means we will have f of x smaller than y will imply f of x smaller than f of y. That equality is omitted in those sense. If you wish, you can refer other authors for those things. Okay, so with the basic understanding of this definition, let us get into a theorem. This theorem tells you that f is a monotonically increasing function. So we are going to prove something for monotonically increasing function now. So it is monotonically increasing on AB. If it is so, then f of x plus and f of x minus exist at every point of every point x of the interval AB. More precisely, your f of x is smaller than or equals f of x plus, this is smaller than, this is bigger than or equals f of x minus, and this is going to be the infimum of f of t, where t lie between x and b, and this is going to be the supremum of t lie between a and x. So this is going to be there. Furthermore, if a less than x less than y less than b, then we'll have f of x plus is smaller than or equals f of y minus. Okay, here you notice that your x is smaller than y, but your f of x plus is smaller than or equals f of y minus. These are the things that we are going to prove in this theorem. Let us see the proof now. Just a minute. Yeah, so proof, we are given that f is monotonically increasing. So let me write it. Increasing on AB. Now let me collect the points set of. So here we are monotonic in the sense we are talking in the set of real numbers. So Let me collect the set of numbers f of t where t lie between a and x. Okay, this is going to be a bounded above set. So this is bounded above by the number f of x. I am saying like this. Why? It is monotonically increasing one. If it is monotonically decreasing one, this set is bounded above by f of a. Okay, these ideas we have seen in the course of sequence and series itself. There we have defined these notions for only for sequences. Sequences is a type of functions in which the domain is only the set of positive integers. Right here, it may be anything. So with this, what we have is that this set has a least upper bound, and let us say supremum of a less than t less than x of f of t. This is nothing but a. We are taking the supremum to be the least upper bound to be a. Okay, this is a notation that we give. So from this we say clearly a is going to be a is smaller than or equals f of x. Right? Now in this theorem, what should we prove actually? We have to prove that supremum is f of x minus. So this is what we must try and prove. Okay. Sorry. So the claim is a has to be f of x minus. Okay. So for which what I am taking is that let me fix epsilon. Next, from the definition of supremum, there exists a delta positive such that a less than x minus delta less than x and big A minus epsilon less than f of x minus delta is less than or equals a. So let us mark this as equation 1. Okay. So this is by the definition of a supremum. Supremum of what? Supremum of the function f of t. So for this we are applying these things and we get this one. Now since f is monotonic, what we have is we have for x less than delta less than t less than x, we are going to have f of x minus delta less than or equals f of t, and this is going to be this. Okay, actually we have written something wrong, so this is a supremum value, so it is a is the larger quantity, right? We shall write this way: f of t smaller than or equals a. So this is what we actually have. So let us mark this as equation 2. So combining these two things from 1 and 2, we get absolute of f of x minus, okay, f of t. So it is a dummy thing, right? F of t minus a less than epsilon for x minus delta less than t less than x. If you take any t in this interval, this is going to happen. So here you may see that is happening. So that is what we have written. This tells you your f of x minus is a. Okay, this is what you have chosen some delta. So this means this is f of x minus. Okay, this completes this part. Similarly, one can easily prove infimum of x less than t less than b of f of t is going to be f of x plus. Hence, both f of x plus and f of x minus exist at every point x in AB, and supremum of a less than t less than x f of f of t, right? This f of t is f of x minus, this is smaller than or equals f of x, and this is f smaller than or equals f of x plus, and this is going to be infimum of x less than t less than b of f of t. Okay, let us mark this as equation 3 because we are going to make use of this. Now let us suppose a less than x less than y less than b. Now we'll have to apply the third equation to the interval x comma b. Okay, so this part alone we are going to check. So this is going to be f of x plus is infimum of, this is the interval, right? So x less than t less than b f of t. Here you see what am I doing is that I am talking about the infimum of, I'll have x here, I'll have t here, I'll have b here. Okay, from this I'm talking about the infimum value. So that is going to occur only at x. If I talk about the infimum of x less than t less than y, which means I have chosen some t between x and y. This is a monotonically increasing function. So whether I talk about the supremum in this interval or this interval, this is going to be same. So let me write that. Okay, and now I'll have to apply the same to a comma y. So here what am I going to get? If you see, this is my a, this is my y somewhere, and this is my x, and I'm going to take some t here. Okay, first initially I am applying a to y. Okay, so this is going to be f of y minus is going to be the supremum of a less than t less than y of f of t. I am going to talk about the supremum, which means if I have my supremum would occur at this place. So I take the supremum of this thing or this thing that is going to be same. So this is supremum of x less than t x less than y f of t. Okay, if you mark this as 4 and 5, we know that infimum of any function is going to be supremum of that function over any interval. Okay, using this fact, equation 4 and 5, what we get is infimum of x less than t less than y f of t is less than or equals supremum of x less than t less than y f of t, and this concludes infimum value is what, f of x plus, and supremum is f of y minus. This completes the proof. Theorem has been proved for monotonically increasing functions. Similar results can be established for monotonically decreasing functions as well. The corollary to the theorem tells you that monotonic functions have no discontinuities of second kind. What do we mean by discontinuities of second kind? That is the mixed discontinuities. One side it goes, the limit does not exist, whereas the other side it exists. Such kind of discontinuity is not permitted in monotonic functions. The next theorem on monotonic functions tells you, sorry, theorem. Okay, we have a monotonic function. So here they have simply given f is monotonic on the interval ab, which means we it is applicable for both monotonic increasing as well as monotonic decreasing. Then the set of points of this interval at which f is discontinuous is at most countable. Okay, let us prove it quickly. So suppose f is monotonically increasing, and let us take E to be the set of points at which f is discontinuous. Okay, so this is the set of points at which f is discontinuous. We have collected the discontinuities of the function f into a set E. Now what we are going to do is that for every x in E, we associate a rational number. That one, let me denote it as r of x, such that f of x minus less than r of x less than f of x. This choice is always possible. Given that f is a monotonic increasing function, so f of the function is not continuous at the point x. If it is given so, we may always find f of x plus and f of x minus. These 2 points always exist. We are not talking about the continuity at those points, but still what we are saying is that, okay, suppose this is my x. Okay, let this be my f of x. So I can find some my f of x plus somewhere here and f of x minus somewhere here. Between these 2 points, I can always find some rational number. If I want, I can find some irrational number too. The reason of choosing rational numbers will be understood once we complete this proof. Because we are going to talk about at most countable. So we need something which relates the countability. That is why we have chosen a rational number. Okay. Once rational number is chosen, then what we are going to see is that, okay, if we take x1 less than x2, of course this will imply f of x1 plus less than or equals f of x2 minus. This one we have just seen in the previous theorem. Since this is happening, okay, since this is happening, from this what we get is r of x1 is not going to be equal to r of x2 whenever x1 and x2 are different. Okay, only because of this, right? If you want, you can do check it. For x1 you can find x1 minus less than r of x1 less than f of x1 plus. Okay, and what, your x2 minus less than r of x2 less than f of x2 plus. From this we get this quantity is less than or equals f of x1 plus. Okay, here you have all of the rest of the things. Here we are able to see very well that r of x1 is not going to be equal to r of x2. So this is I think I must have written these things in some other color. Okay, so okay, if you want, let me do it completely too. Okay, as a part of a proof, let me write it. Since x1, this is happening, f of x1 minus is less than r of x1 is less than f of x1 plus, which is less than or equal to f of x2 minus, which is less than r of x2, which is less than f of x2 plus. This tells you x1 not equals x2 will imply r of x1 not equals r of x2. Okay, this, let me write it in the next page. Hence, what we have done is that we established a 1-1 correspondence between E and a subset of rational numbers. So how did we achieve it? Let us go back and see the things over here. Let me write it in another color. Here if you see this R, this X is taken in E, which means you may consider this R to be a function E to Q. This is what, because for every X in E we associate a rational number R of X. So X you take from here, this is a member of Q. This is what we have done. Okay, and this statement tells you that your function R is 1 1. Okay, once you have 1 1 function, remove those points. That is, if you restrict your mapping to the range alone, don't consider the entire domain. If you restrict your mapping to the range alone, you will get this function to be 1 1 and on 2. So the codomain is the set of rational numbers. If you take the subset of that is only the range, that is what we have mentioned here as a subset. Okay, so we established a 1 1 correspondence between these two things. We know the set of rational numbers is countable. Here we are talking about the set of subset of rational numbers. Hence, the set E is at most countable. If it is in 1 1 correspondence with the set of rational numbers, the entire rational numbers, then we conclude that it is a countable set. But it is a subset. So here you will have to establish a composition of mappings which takes every element of E to the some subset of set of positive integers. Okay, I am not telling all those things in detail just because you people are very well aware of these things, right? And this completes the proof. Okay, next the remark that I would like to make here is there are two remarks. The discontinuities of monotonic functions need not be isolated. The second one, given any countable subset E of AB, we can construct a monotonic function which is discontinuous at every point of E and at no other points of AB. So what they are trying to say is that you can always construct a monotonic function which is discontinuous in the countable set only at the points of that countable set. At no other points it is not actually, only at the points in the countable set it is discontinuous, and at all other points it is being continuous. That is what they have given as a remark. Thank you.